Hi Vijay, how are you?
Fine, thank you. How are you, Ravi?
Fine.
Nice.
Yeah.
Now everybody is on mute. Srivastava sir, may I start?
Yes, please.
Thank you, sir. Life and time are the world's best teachers. Life teaches us the use of time, and time teaches us the value of life. A very marvelous and a very charming and a hearty very welcome to our eminent speaker, Professor H.S. Mani, all the panelists, members of Delhi State Science Teachers Forum, all the members of Indian Association of Physics Teacher, Regional Council 1, and my dear participants. Myself, Poonam Jain, the member of Executive Council, Indian Association of Physics Teachers, welcome you all on the behalf of IAPT for the second vibrant session of the online webinar series jointly organized by IAPT RC1 and DSSTF. Before beginning with the formal session of the day, this is to inform you that this session is being recorded and streaming live on YouTube and Facebook. It is our pleasure to host more than 500 participants via Zoom and approximately same number via YouTube and Facebook. All the panelists are requested to kindly mute their mics during the session. Now, I request Dr. S.K. Singhal for the further proceedings. Over to you, sir.
Thank you, Poonam ma'am. Very good morning to all of you, all present here. Myself, Dr. S.K. Singhal, Treasurer, IAPT RC1, Delhi, Haryana. Welcome to Professor H.S. Mani, all panelists and participants in IAPT online lecture series. Today, Professor H.S. Mani will deliver the 6th online lecture on electrostatics part 2. This program has been organized in collaboration with Delhi State Science Teacher Forum. Please note, for the certificates, attendance is mandatory in Google Form. The link of the Google Form will be shared in the chat box and YouTube. All participants are requested to post their questions in the question answer box only. Those are unable to join through the Zoom are requested to join through the YouTube and Facebook Live. They are also requested to write their correct name and email in the comment box. Now I request Dr. M.S. Bhandari, Secretary, Regional Council IAPT RC1 to deliver the welcome address and to give the introduction about the IAPT RC1. Bhandari sir.
Thank you, Dr. Singer. Good morning, everyone. Though it's customary, but for me, it's a privilege to give an introduction about IAPT. First of all, I would like to welcome and compliment our distinguished speaker, Professor H.S. Mani, on behalf of IAPT and participants for the program today and the previous one. Your previous lecture on the electrostatics has been very intuitive, informative, and inspiring for all of us. We all thank you for that from the core of our heart. I welcome our honorable guest, Professor Ravi Bhattacharya जी. अगर मैं हिंदी में कहूँ तो एक बहुत ही एप्रोप्रिएट, एक बहुत ही सटीक शब्द रवि भट्टाचार्य जी के लिए है. ये हमारी आईएपीटी के पुरोधा हैं. ये काफ़ी लंबे समय से आईएपीटी के साथ जुड़े हुए हैं और एशियन फिजिक्स ओलंपियाड का कार्यभार इन्हीं के पास है और कई वर्षों से ये उसका वहन बड़ी दक्षता के साथ कर रहे हैं. और जो उसमें एक गुप्तता और एक बहुत ही एक स्टैंडर्ड को मेंटेन रखने की जो क्षमता है रवि भट्टाचार्य जी में, वो है. वी थैंक यू फॉर दैट सर. देन प्रोफेसर विजय सिंह जी, प्रेसिडेंट आईएपीटी सेंट्रल बॉडी. अब इनके बारे में भी हमारे पास कहने को मैं नहीं समझता कि बहुत एप्रोप्रिएट शब्द हैं. इनको भी हम पुरोधा कह सकते हैं. और सर की गाइडलाइंस में और सर के नेतृत्व में आईएपीटी ने बहुत से आयाम हासिल किए हैं और आईएपीटी आज जिस मुकाम पे है उसके लिए बहुत कुछ दारोदमार प्रोफेसर विजय सिंह की भी जाता है. वी थैंक यू फॉर दैट. एंड वी आर हैविंग विद अस प्रोफेसर टी.के. पांडे, प्रिंसिपल एनसी जिंदर पब्लिक स्कूल. सर का भी कंट्रीब्यूशन आईएपीटी में कम नहीं है. अक्सर अगर हमें किसी चीज़ की आवश्यकता होती है, कभी कोई हमारे पास स्थान की कमी होती है प्रोग्राम कंडक्ट करने के लिए, तो सर का बहुत ही सहज भाव से हमारे रिक्वेस्ट को एक्सेप्ट करना हमारे लिए बहुत सम्मान की बात है. मैं वेलकम करता हूं डॉक्टर डी.के. पांडे जी का. इसके साथ ही हमारे साथ है प्रोफेसर वी.के. शर्मा जी.
अच्छा, यू हैव ऑलरेडी ज्वाइन.
ये सब हमारे ऑनरेबल गेस्ट हैं और हमें इनका वेलकम करता हूं. इसके बाद ही अब मैं आपके बारे तो कुछ शब्दों में आईएपीटी के बारे में इंट्रोडक्शन दूंगा. Established in 1984 by late Dr. D.B. Khandelwal, IAPT today has grown into a major and well-reputed organization only because of the efforts of its EC members and its life members from India and abroad. IAPT RC1 is a local chapter of Delhi and Haryana. IAPT RC1 conducts a large number of activities every year. Some of the activities are Professor Vedratna Memorial Lecture, annual convocation in which papers are invited on different topics, regional competition in innovative experiments, training workshops and hands-on approach of teaching physics, lectures by eminent scientists and educationists, and a very important work that we do in collaboration with DSSTF. We hold a paper discussion of the exam conducted by CBSE. We prepare a report and marking scheme and submit it to the CBSE, recognized and appreciated by the board. IAPT central body conducts national standard examinations like National Standard Examination in Junior Science, national standard examination in physics, chemistry, bio and astronomy for +2 level students. Then there is Asian Physics Olympiad, an annual physics competition for high school students. And for undergraduate students, there is an examination, National Graduate Physics Examination. Another important venture of IAPT is Anveshika, to impart experiment-based physics education in school and colleges. Anveshikas are running in the country, National Anveshika Network of India, better known as NANES, interaction sessions with students, short and long-term teachers training programs, workshops to develop new teaching demonstration and other activities. There is an ELCB program also. Under this program, life members are offered quality physics books at a considerable discount in order to showcase IAPT activities and innovative ideas of the work of members and to keep updated with the latest developments in the world of physics. IAPT brings out a IAPT bulletin regularly. Students, there is a journal, the Prayas, which is published by IAPT. So these are the some prominent activities everywhere conducted by IAPT. With this, I welcome again our distinguished speaker, honorable guests and respective participants. Thank you very much.
Thank you, Bhandari sir. As today's program is also organized in the collaboration of Delhi State Science Teacher Forum. So now I request Mrs. Pragya Kiran, General Secretary, Delhi State Teacher Science Forum, to give introduction about the forum. Pragya ma'am.
थैंक यू सर। मैं भी IAPT जैसे बहुत से काम करता है, तो दिल्ली स्टेट साइंस टीचर्स फोरम भी एक ऑर्गेनाइजेशन है जिसके अंदर प्राइमरी टीचर से लेकर के यूनिवर्सिटी टीचर्स और बहुत सारे साइंटिस्ट जो IAR पूसा से या NPL या DRD से हैं, लोग NCERT और ये NCERT और SCERT से भी लोग हमारे साथ जुड़े होते हैं। तो ये जो है एक बहुत हेट्रोजीनियस ग्रुप है जिसके में हम काम कर रहे हैं और ये 1979 में इसकी स्थापना हुई थी और जब इसकी स्थापना हुई है उसके बाद से हम बहुत सारी एक्टिविटीज करते हैं जिसके अंदर हमने शुरू में जब हमने स्टार्ट किया तो हमने साइंस टीचिंग कैंप्स लगाए और इन कैंप्स में हमने 8वीं से 10वीं तक के बच्चों को हैंड्स ऑन एक्टिविटीज के करके बहुत सारे उनको करे जिससे कि उनका इंटरेस्ट साइंस सब्जेक्ट में डेवलप हो और उनका साइंटिफिक एटीट्यूड डेवलप हो, साथ ही साथ वो आगे आकर के +2 में ज्यादा से ज्यादा बच्चे साइंस को ऑप्ट कर सके। ये हमारा एक मिशन था कि हम इसको ऐसा करें और हमने बहुत सालों तक इसको हम कर रहे हैं, बहुत सालों से। और दूसरा इस हम लोग एक साइंस ओपन टेस्ट भी ऑर्गेनाइज करते हैं और इस टेस्ट के अंदर रिजल्ट होने के बाद जो कि ये जो टेस्ट है ये बहुत ही जो लोग NCERT, SCERT या डायरेक्टरेट ऑफ एजुकेशन से एसोसिएटेड हैं उन लोगों के गाइडेंस में ये सारा टेस्ट पेपर बनता है और उसमें जो बच्चे टेस्ट देने आते हैं उनको हम एक मॉक टेस्ट भी देते हैं जो कि उनको 10th क्लास के बोर्ड के एग्जाम्स के लिए बहुत बेनिफिशियल होता है, टीचर्स के लिए भी और बच्चों के लिए भी, जिससे कि उनके बोर्ड की तैयारी भी हो जाती है और ये आगे जो कभी गवर्नमेंट स्कूल के बच्चों को बहुत ज्यादा वो नहीं मिलता है। अब तो खैर थोड़ी स्थिति चेंज हुई है लेकिन पहले से ये था कि पब्लिक स्कूल जो पब्लिक सेक्टर के या कॉम्पिटिटिव एग्जाम्स होते थे उनमें वो लोग बहुत ज्यादा पार्टिसिपेट नहीं कर पाते थे, तो उनको एक ये मौका मिलता था कि किस तरह से हम वो वाले क्वेश्चंस को अटेम्प्ट कर सके, बच्चे अटेम्प्ट कर सके इन क्वेश्चंस को। इसके बाद हम एक फंक्शन भी ऑर्गेनाइज करते हैं उन बच्चों के लिए जो मेरिट लिस्ट में आते हैं और उनके साथ हम टीचर्स को भी अप्रिशिएट करते हैं जिन्होंने इसको बच्चों को गाइड किया इसके अंदर। और ये हमारा एक प्रोग्राम रहता है। हम लोग टीचर्स के लिए बाई एनुअल साइंस कांग्रेस भी ऑर्गेनाइज करते हैं जिसमें टीचर्स जो हैं अपना पेपर प्रेजेंट कर सकते हैं और अपनी इनोवेशंस बता सकते हैं। एक प्लेटफॉर्म है जो कि उनको सारे लोग दिल्ली के टीचर से या आसपास के टीचर से कनेक्ट करता है। और जैसा कि IAPT +2 पे करती है, हम लोग क्लास 10th और फिजिक्स, केमिस्ट्री और बायोलॉजी सबका क्रिटिकल एनालिसिस करते हैं क्वेश्चन पेपर का। और जो कि हमारे सेशंस जो हैं वो उसके अंदर जाते हैं, CBSE में हम उनकी रिपोर्ट सबमिट करते हैं। और उसके बाद जो है ये सजेशंस जो हैं बहुत सारे बच्चों को, जो हमारे इनकॉर्पोरेट होते हैं CSE से, उससे बहुत सारे बच्चों को बेनिफिट होता है। हम लोग सेकंड सैटरडे ऑफ द मंथ को स्टडी सर्कल मीट्स ऑर्गेनाइज करते हैं और उसके अंदर मासेस के अंदर किस तरह से साइंस को हम पॉपुलराइज कर सकें या छोटे छोटे मुद्दे उठा करके हम वो बात करते हैं। जो हमारे फंक्शंस होते हैं, जो ऑर्गेनाइज करते हैं, उसके अंदर हम लोगों को मौका मिलता है, बहुत सारे लोग जैसे कि APJ अब्दुल कलाम है, स्वामीनाथन है, डॉक्टर कोठारी हैं, प्रोफेसर यशपाल हैं, ये लोग हमारे फंक्शंस में आए और हम लोगों ने उनके साथ जो है काफी कोऑर्डिनेट किया और इंटरेक्ट करने का मौका मिला। और इन लोगों से हमें इंस्पिरेशन भी मिलता है कि हम आगे अपने जीवन में कैसे काम करें और किस तरह से हम आगे बढ़ें। और हमारा साइंस का रिप्रेजेंटेशन जो साइंस के लोग हैं वो नेशनल एजुकेशन पॉलिसी में भी रहा है और न्यू एजुकेशन पॉलिसी में भी है। हम लोग डायरेक्टरेट ऑफ एजुकेशन के साथ भी मिलकर बहुत सारे काम करते हैं, जैसे कि बहुत सारी एक्टिविटीज हैं रूरल एरिया के लिए, साइंटिफिक किट्स बनाना जहाँ पे बहुत अच्छी लैब्स नहीं है, और ये जो है क्लासरूम में भी जाके टीचर्स कर सकते हैं। अगर इतने सारे बच्चे हैं, हर एक बच्चे को लैब में आने की फैसिलिटीज नहीं है। जो डायरेक्टरेट ऑफ एजुकेशन है, जैसे कि साइंस कांग्रेस, इंस्पायर अवार्ड और स्टेट, डिस्ट्रिक्ट और जोनल लेवल पे जो साइंस एग्जीबिशन होती हैं, वो भी हम लोग को पार्टिसिपेट, हम लोगों को बोला जाता है कि किस तरह से आप इसको हेल्प करिए और ये कार्य करिए। हमारी एक साइंस मैगजीन भी है, उसमें भी साइंस टीचर से बोलते हैं कि वो अपने आर्टिकल्स वगैरह दें। हम भी जैसे IAPT के बारे में बताया, और हम लोग इसलिए बता रहे हैं कि इस मंच पर इस समय इतने सारे लोग कनेक्टेड हैं, वो जो भी एक्टिविटीज से जुड़ना चाहें वो हम जुड़ सकते हैं और हम इस मुहिम को आगे बढ़ा सकते हैं। और जितना कारवा बढ़ता जाए उतना अच्छा रहता है। और दर्पण में जो लोग अपनी देना चाहते हैं वो हमारे से कांटेक्ट करके, हमारे से बात करके अपने आर्टिकल्स दे सकते हैं। और इसके बाद हमारा लॉन्ग एसोसिएशन है IAPT से, जो कि हम लोग बहुत सारे आपस में करते हैं। डॉक्टर पांडे हैं यहाँ, तिवारी सर हैं, जैसे कि अभी सर ने बताया कि डॉक्टर पांडे के स्कूल में भी हम बहुत सारे फंक्शन हमने ऑर्गेनाइज किए हैं। थैंक यू फॉर दैट सर। और हमारे क्वेश्चन पेपर एनालिसिस में हम तिवारी सर के स्कूल में भी जाते हैं। तो हम लोग इस तरह से एक दूसरे की हेल्प करते हम काम करते हैं। और इस समय ये पैंडेमिक चल रहा है, तो हमने कुछ अलग वेबिनार करके ही लोगों से कनेक्ट करने की कोशिश की है। और हर समय डर रहता है कि कहाँ हम इकट्ठे कैसे करें, तो हम लोग इस तरह से काम करते रहते हैं। अंत में मैं कहना चाहेंगी, क्यों डरे जिंदगी में क्या होगा, क्यों डरे जिंदगी में क्या होगा, हर वक्त क्यों सोचे कि बुरा होगा, बढ़ते रहे मंजिलों की ओर हम, कुछ भी न मिला तो क्या, तजुर्बा तो कुछ नया होगा। तो ये हम नए तजुर्बे के साथ आगे बढ़ रहे हैं। थैंक यू।
Thank you, Pragya ma'am. Beautiful shairi that you told, and a very useful information about the Delhi State Science Teacher Forum, and that many things that we were not aware about that information given by you. Now I request our President, Professor VP Srivastava sir, IAPT RC1, to introduce the distinguished speaker of today's lecture. Professor VP Srivastava sir.
Namaskar. Good morning, everyone. Before I start, let me welcome a distinguished and senior scientist from Inter-University Accelerator Center, New Delhi, Professor Ajit Kumar, BP, who has just joined us. Thank you very much, sir, for joining us. It is my pleasure and honor to introduce Professor Mani. I have known Professor Mani since 2006, when he was a team member to review and finalize the manuscript of NCERT Class 12 Physics Textbook. Professor Mani obtained his BSc and MSc from Delhi University, and his doctorate degree in physics from Columbia University, USA in 1964. He worked as assistant professor in University of Michigan before joining IIT Kanpur in 1969. The primary focus of his research work has been in high-energy phenomenology. His significant contributions spread over diverse areas of high-energy physics, like electroweak interactions, quantum chromodynamics, and physics beyond the standard model. Besides research, Professor Mani is known to be a passionate teacher. Professor Mani became the director of the Mehta Research Institute, now known as Harish Chandra Research Institute, Allahabad, in 1992. After completing his term as a director in 2001, he has held several distinguished positions, such as a visiting scientist at the S.N. Bose National Center for Basic Sciences, Kolkata, Professor Rajaramana Fellow at the Institute of Mathematical Sciences, Chennai, Jawaharlal Nehru Chair Professor at the University of Hyderabad, visiting professor at the Indian Institute of Science Education and Research, Mohali. Professor Mali, along with Professor G.K. Mehta, has written a popular book entitled Introduction to Modern Physics. Since 2009, Professor Mani has been an adjunct professor at the Chennai Mathematical Institute. Besides teaching at IIT Kanpur, Professor Mani has been contributing to science education throughout the country at various platforms. These include training high school students, giving lectures in SERC schools. Professor Mani has contributed immensely to the Olympiad program in physics in India by giving lectures to the selected students and serving as the co-chairman of the Asian Physics Olympiad in 2012. Professor Mani has received many honors during his illustrious career. He is the fellow of the Indian Academy of Sciences, Bengaluru, and the National Academy of Sciences, Allahabad. Professor Mani received the DAE C.V. Raman Lecturership by the Indian Physics Association in 1998 and the M.N. Saha Award by the UGC Hari Om's Ashram Trust in 1999. He was also awarded the Distinguished Teacher Award by IIT Kanpur in 2007 and the INSA Teacher Award in 2013. IIT Kanpur also conferred upon him the award of the Institute Fellow for the year 2017. Dr. Mani has inspired many generations of students and teachers in his 50 years of career and to do good physics. We are sure, sir, you will continue to do so in years to come. From his lectures, you will see what it means to do good physics. I invite now Professor Mani to deliver his second part of his lecture on electrostatics. Over to Professor Mani, sir.
Unmute yourself. Mani sir, kindly unmute yourself.
I unmute. I thought it is unmuted.
Yes, sir. Now kindly screen share.
You can hear me, right?
Yes, sir. Yes, sir.
Now I will start my lecture by saying good morning. And I have some things regarding questions which came to me. And I would like to respond to that. 1 second. Let me make sure I am in the presentation mode. All
so
right.
Kindly share your screen first.
Oh, I didn't do that. Okay.
No, sir.
I'm sorry.
No problem, sir.
Okay, I have to share first here and then share. Right now I can go to that mode. I go to the presentation mode. Now can everybody see? Is it clear?
Yes, sir.
Some of them tell me that my air conditioner makes noise. If it does, tell me, I will shut it off.
Right now it is fine, sir.
Right now it is fine. Sometimes it starts making noise. If it does, please let me know. If it interferes, I will shut it off. Is it okay?
Sure, sir. Sure, sir.
Okay.
Sure.
Okay.
Thank you,
Now,
sir.
fine. Now, one question which was asked, and it is a very important question, I should answer that. When I wrote the number of lines of force N in an area dA, I wrote it like that. N is just dimensionless where there is dimension here. How come this equation could be correct? So the person who asked this question is correct. However, one can match the two by adding a dimensioned constant here. I can make the dimension constant by appropriate choices to be unity. None of the things that I discussed mattered on this. Perhaps the correct way I should have said is number is proportional to E dot dA. It really is not very material for main things here. Lines of force start from positive charge and go to infinity or end in a negative charge. Lines of force cannot end in midair. Next is lines of force cannot cross. None of these three statements which I used depend upon the choice of K. Hope this clarifies, and our interest was in understanding the charge distribution on a conductor using the concept of line of force. This is one. And next is a very interesting question was asked regarding Earnshaw's theorem. Let me remind you what Earnshaw's theorem was, that if you have a place where electric field is zero, and if I keep a test charge there, the force acting on it will be zero. So it will be in equilibrium. However, it is not a stable equilibrium. And I illustrated this with examples of a midpoint between two charges plus Q and plus Q. I showed which paths lead to unstable movement. Now, the question that was asked is that I place 8 charges on 8 corners of a cube. The field at the center of cube is 0. Which is the path which leads to the instability? I have not yet worked out the details. I have sent a message, email message to the person who asked this question, and I had suggested a method of tackling it. I did not want to complete it myself, expecting some participation. Let's see whether this works out right. Then I have heard from friends that many questions could not be taken up because of time constraint. So please send me email, hsmoney@gmail.com, and we'll answer them, of course, to the best of my ability within 1 or 2 days. This way, this entire exercise, which has been taken up, thankfully, by Ved Srivastava and his entire team, they have been doing a wonderful job, taking so much effort. We will be able to show some success in whatever the efforts they are putting in. So this is the thing which I wanted to show. Now, let me go to the main topic today. I will just go into the presentation mode. All right, I'm repeating my good morning in the slide, which is good morning to all of you. And the things that I'm going to talk about today are: one is method of images, second is electric dipole, and the third will be dielectric medium. I have chosen these topics by following the textbook of NCERT, and after having discussion with Professor Ved Srivastava, that what we should try to concentrate is review some of these material and perhaps add a few points here and there, which would help the main participants in their teaching. So now I go here. In the last lecture, we discussed the uniqueness theorem. What does the uniqueness theorem state? Supposing I have charges someplace and I have conductors, and I tell the potential of the conductor. Some is V equal to V1, V equal to V2, and so on, and charges are fixed. If you are able to find a solution, there is no other solution. That is it. So if you are able to make a guess of a solution by appropriate meaning, thinking here and there, then, and if it works out right, what do I mean by works out right? The charges as given, the potential on conductors as given. If they match, then that is the answer. So this is the statement coming from the uniqueness theorem, and it's a big help. I don't have to worry about anything more as far as that question is concerned. So I will let you read what is written here, and I will wait for a few minutes or so for this to be read. Okay, I think I'll go to the next slide now. It again says the same thing I had said. I will wait for a few seconds. The example that I'm going to take is a point charge in front of an infinite conductor, which is earthed. here it is. I have a plate, and this side is all conductor. So electric field there is 0, and it is earthed. When it is earthed, the potential is 0. Incidentally, there is one point about this earthing which I should mention. We always assume that at infinity, the potential is 0 in electrostatics. Yeah, I could have assumed it to be some constant. All the potentials will go up by a constant. When we do gravitational, the V equal to 0 is usually the floor or some other place which is not as well fixed as in electrostatics. It really doesn't matter. We think of Earth as so large, a small exchange of charge and there will not change the potential of the Earth very much, and we keep that as standard. That's what is meant by Earth. If you want to say it strictly mathematically, I will say the potential there has been kept to 0. How? We cannot say. It may be because I take a wire very far away, and that is the answer. And I have a charge Q here at a distance d from the conductor, and x is that direction. The question is, I must find out the field here. Okay, charge in front of a conductor, field inside here is of course 0, potential here is constant, and that is V equal to 0. Need the field in this region. This is the question. So I go to the next slide, and the answer is this. I put a charge Q here and a charge minus Q here at a distance d inside. This is called the mirror. Treat this as a mirror, and this is the image. P prime is the image of P. And this is minus Q. Let's see why this works. Now notice any point on the conductor is midway between P prime and P. So the distance, supposing this is a point here, this distance is the same as that distance. The two are equal. So the potential here we know how to calculate at a distance r. It is Q by 4 pi epsilon naught times 1 by r. So that will be the potential due to this. The potential due to this will be minus Q by 4 pi epsilon naught times 1 by r. But r is the same for both of them. Therefore, this comes with the minus sign. They cancel out. So the potential here is 0. Any point here will be equidistant from P prime and P. So the potential here is 0. I'm through. I've kept the potential 0, and there is one charge here, and that's all. So as far as if I want to find out the field here, I take this Q and minus Q and find the field here. Not for this place. This place is 0. For this place, I don't take Q and minus Q. That's not right. This works for this region where x is greater than 0. For x less than 0, we already know the answer. Answer is E is 0. So now let's do the math. Here, let the charge be at di. I, of course, is a unit vector along x-axis. Then the image charge is minus di, which has a value minus q. I have already discussed this, so let me just go to the next slide. The electric field is given by, at a point r is xi plus yi plus zk. And notice the charge q is at di. So I write down r minus di. I have x minus di written here, yj and zk. So r vector minus di vector is written explicitly here. Similarly, r vector plus di vector, this just becomes plus. This is the distance from the image charge. This is the distance from the actual charge in front of the or the vector. I shouldn't say the distance, the vector. The distances are given here. I just have to take the square root and take x minus d whole squared and y squared and z squared. The same story here, except minus d becomes plus d here. So this is the expression, which is, notice r minus di is the vector divided by r minus di cubed, minus, because the charge, the image charge is negative, it is r plus di by r. So this is the electric field at the place r vector. I'll just wait for a second. Okay. Now consider a point A on the conductor, which I've already discussed, which is x is 0 on the conductor, y and z. Now what is r minus di? It is X is 0, so this is only minus di, yj plus zk. R plus di is di plus zk. So let's look at this distance, r minus d. This is the expression yj zk minus di. Yj zk minus di. I take the mod and take square root of that will be y squared plus z squared plus d squared. Then this is the same whether this minus d is plus, because I always get a plus d squared here. This, of course, we had already seen. The plate is a midpoint. Any point of the plate is on the line normal to PP prime midpoint drawn. Thus, the field there is given by yj plus zk minus di, and the denominator is y squared plus z squared plus d squared. X is now 0. Here, no, let me go to the previous slide. Notice there is x here. X on the plate is 0. So I just get d squared plus y squared plus z squared, d squared plus y squared plus z squared. So the denominator is the same. Now there is a minus sign. So the term yz plus zk, yz plus zk cancel out, and I'm left with minus 2 qd 4 pi epsilon naught y squared plus z squared plus d squared to the power 3 by 2. Okay, I'll just wait here to make sure that people are comfortable with the algebra. Now, we had seen in the previous talk, the electric field on the surface is given by sigma by epsilon naught n cap. Let me recollect how this happens. Supposing I have a plate, let me just hold on. I will mute it for a minute and then show me. Can you people see me? Hello?
Yes,
Hello,
sir.
can you see me?
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes, sir.
If I show this, you can see this. Hello, can you see this?
Yes, sir. Yes, sir.
We can see you, sir. We can see you.
All right.
Yes,
Yes,
sir.
sir.
Now,
Yes.
take a point here. I will not do all the algebra again. And this, think of this as a conductor. And think of a small surface here and do a pillbox. Part of it inside, part of it outside, and let this area be unity. Okay? Then the flux, we know the field has to be normal to the surface. Field cannot be tangential for in electrostatics. So inside the field is 0. Outside, if it is E, the amount flux will come out will be E. And the charge inside a unit area here is sigma. So according to Gauss's theorem, E is equal to sigma by epsilon naught. And the vectorial direction is normal to it. So that is the equation that I have written here. Let me see whether I have got out of presentation mode, full screen presentation. Okay. So that, where am I? Here. So now I have already calculated E. Here is my E. E is here. So I can now get the sigma on the surface. I know how much charge is there on the surface. I equate E from the previous slide, and I have written down exactly that expression here. So epsilon will cancel. Sigma works out to be this expression here. It's a very interesting expression. Notice that where is the maximum charge density going to be? When the denominator is the smallest. When is the denominator smallest? When y and z are 0. And so it will be q minus q by 2 pi d cube will be there, d squared. So that will be the, and as I go on away from the origin, where x equal to 0, y equal to 0, z equal to 0, y squared plus z squared will increase. So the charge density will go on decreasing. And this means that the maximum lines of force, notice the charge density is negative. So from Q, the line of force which will start will end on the plate. We will see how much of them will end on the plate. We will see that very soon. So the one near the origin, the lines of force will be more dense. And as we go along, the lines of force will become smaller and smaller because this sigma is smaller and E on the surface is also smaller. Now we write S as the distance from the origin here as square root of y squared plus z squared. And notice it really does not depend upon y and z separately. Any direction along y and z which satisfies y squared plus z squared is constant will have a equal. And that's because of the cylindrical symmetry that I have about the x-axis. If I rotate the entire system about the x-axis, Q does not change. The plate goes into itself, so nothing changes. So the density must remain the same. So that's what happens. So I can write down sigma 0 yz as sigma 0 s is minus qd by 2 pi s squared plus d squared to the power 3 by 2. The charge density is negative and decreases as we are moving away. We have already seen this as s increases and sigma decreases. The lines of force from Q on the plate go and hence on the negative charge and on the plate. Okay. I will wait for here for a few seconds just to be sure everything is understood. Now let's calculate the total charge on the plate. How do I do that? I know the charge density at x, y, z. I have to integrate over all the charge densities on the y and z. So I write down minus qd by 4 pi. This is the charge density expression. dy going from minus infinity to plus infinity. dz going from minus infinity to plus infinity. It's a double integral because I have to do a surface integral. There are two things I have to integrate over y and z. And the quantity I have to integrate is d squared plus y squared plus z squared. To do this integral, it is easily performed if I go to polar coordinates. I write y as s cos theta and z as s sine theta. We normally use x and y. Here I am using y and z because that is the plane in which we are. We are in the yz plane and s is square root of y squared plus z squared. So if I do that, I know what is the area in polar coordinates. It is s d theta, the arc length, times ds, the length of the radius, that one which is there. Normally we write it as r d theta times dr. Instead of r, I'm using s, so it is s d theta ds. S is going from 0 to infinity and theta is going from 0 to 2 pi. Thus the total charge that I have is given in this expression. That it's again a double integral. Now the double integral is with respect to theta and s. So I write down minus qd by 2 pi here, and I write d theta going from 0 to 2 pi and s going, this becomes s ds is here, d theta is here, and s squared plus d squared cubed. Notice this integral this is easy to do. This will just give me 2 pi. There is no theta dependence here. So in the 2 pi and 2 pi will cancel. This integral is also not difficult to do because I can write down ds s ds as d of s squared by 2. And I have s squared here. So that is a standard integral we all know how to do. So I will write that down here. It is the integral over theta I have already said, as there is no theta dependence of the integrand. And to perform the s integral, we introduce a variable u equal to s squared. Then du just coming from here is 2s ds. And we can write the expression of the total charge on the plate as q plate minus q by 2 pi 2 pi and half u s squared is u plus d squared. Du by u squared, I know how to do that integral. This is cancelled. It is u plus d squared to the power minus a half because du by u, this is minus a half and 0 to infinity. When I do that, when u goes to infinity, this gives me 0. This gives me with minus sign coming from 0 plus, u is 0. So I get this 2 will go up and I will get d here and I get minus q. This means the total charge on the plate is minus q. All the lines of force starting from plus q will end on the plate. Even if it's very strange, even if it starts in this direction, it is going to bend somewhere and end on the plate. except for one line which you might think of going straight, and that goes to infinity, but one line doesn't matter. It's all the lines which are all going here to infinity. This is the value on the plate. So the total charge on the plate is minus q. Okay, now I'll go to the next slide. Now I'm going to calculate the force on the conductor. Notice the charge q will attract the conductor. Unless I hold the conductor, conductor will not be in place. Why? Because it is negatively charged and I have a positive charge. Or if I hold the conductor, the charge will try to move to the plate. So I have to hold the charge. One of the two, both of them have to be held. Otherwise, one will move towards the other. Okay. The force F on a surface charge sigma on a conductor is given by sigma E by 2. This is very important. It is not sigma times E. It is sigma E by 2, where E is the electric field at the surface. Why is there a factor of half? This is something we discussed it last time. I would like to repeat it because this is a very important point. If the electric field that is built near the surface of a charge comes from two parts. One, which is from the nearest part of the surface, and because when it is close, the field will be large, and from the rest of the conductor. This was the last thing I did in the last lecture. And the two are equal because the electric field due to the charge nearby, let me again show here. Let me think of this. Supposing I am thinking of this as my near part here, the field due to the near part will be in that direction. Think of this as a charge sheet. Sigma will be, it will be in that direction. And there'll be a field due to this inside. That inside field has to be cancelled by the field here. The rest of it, therefore, is producing a field outside of equal length. And the field outside is a combination of the field due to this bit and the field due to the rest of it. They are equal. If they are equal and cancelling, the field due to very far away does not change very much when I move from just inside to just outside. So the field here, I don't calculate the force on a particle due to the electric field produced by itself. I only calculate it due to all other charges. All other charges produce a field which is equal to the one produced here. So the total is E. So I must use only E by 2 to calculate the force on this. This is a very important point, and you should keep that in mind. I have written that here. I will just wait for a few seconds so that people can read it. All right, now let me go to the next slide. So I can calculate the force. Again, to do the same thing, I have to integrate over the entire plate. I do it in polar coordinates. I will not repeat the algebra. It is very simple. Same way, sigma, I have already calculated. E, I know. So I substitute all that. I will leave the algebra here, and it is S ds by here. Sigma we had calculated as 3 by 2. E was also 3 by 2. That's why I get cubed. And I can again perform the integral. I will not do the answer. I'll just again integral, and the answer is the force on the plate, charge Q. Charge attracts the plate with this value. We interpret this in a very simple way. I had an image charge at minus d. The charge is Q. So the force between the two is Q squared by 4d squared, apart from the factor this 1 by 4 pi epsilon, which keeps hanging around all the time. So one just gets the force as if the entire charge is concentrated on the image. The plate, the force on the plate is uniformly distributed. It is not at one place, but it can be, when I add all the force, it is the same as the force I will see from the image charge on Q. So this is the other thing which one has. So we have essentially solved this problem completely. Now, there are other examples. I can now think of two plates like that, and I have Q here. I'm not going to work out the details. E here, this is a conductor. E here is 0, V is 0, E is 0, conductor. All this is conductor. I have Q. So how would you do? What will be the guess? Guess would be, I put an image charge here, negative. I put another image charge here, negative. But I need to put one more image charge here, and that will be positive. Okay. So I'll go to the next slide. You will see that negative charges are blue, positive charges are red. That's the way I write it. Now let's check whether this works. Let's take this plate. This plate minus Q and plus Q give me 0 here. Field. Sorry, potential. Potential I get 0. Minus Q because it's equidistant. So these two added up give me 0 here. What about these two? Again, this is minus Q, this is plus Q. And they are equidistant here. So these two add give me 0 here. These two add give me 0 here. So all four of them added together gives me 0 here. What about this plate? This Q and minus Q gives me 0 here. And this minus Q and this plus Q gives me 0 here. So all these four together ensure that the potential here is 0 and the potential here is 0. I'm through. There is nothing more to do. I know the answer. So if I want to calculate E, which I'm not going to do, I will have to write down field due to this, field due to this, field due to this, field due to this, add up. I will find out what sigma is here, all that job can be done. I can find out what the force acting on it and so on. I will just wait here for a second and make sure that you have understood this. Now you can play games with it. I can have two plates making an angle 60 degrees. Then you can think of putting charges and so on. And so long as you are able to make the boundary conditions satisfy the boundary conditions, the problem is solved. Thanks to the uniqueness theorem. There are few more problems that can be solved by method of images. Few examples are charge in front of a conducting sphere. This involves some amount of geometry, which we learned when we were in school, but I don't know whether it is being taught now because teaching geometry has had a major revision and it keeps changing. Line charge in front of a conducting right circular cylinder. The axis of the cylinder is in the same direction as the light charge. This also uses some geometry. And again, it's a very interesting problem, but the basic idea is the same. Perhaps an average student might find this very challenging. And so the idea we need not, these are not presented there. The next one is even more challenging, is two right circular cylinders with their axes parallel. This can be done. And there are many other problems. Same idea is the same. Guess the solution using the idea of geometry. And there are more advanced methods as applying complex variables to solve many such interesting problems. People have solved it for ellipse, ellipsoid, and so on. And they involve understanding the analytical properties of the field and the potential, which is something which is taught in the master's program. And so not for school, but even then one should know that there are other methods. That finishes the topic of method of images. I'll just wait here so that people can just collect their thoughts. Okay, now I go to the next topic, the electric dipole. I have two charges here, minus Q and plus Q, separated by a distance d, and this is pointing along the y-axis. And I want to write the field here at a point P. The field there is, we have already done this kind of a thing earlier, is given by q by 4 pi epsilon naught. I take that out. And then with q, it will be r minus dj. This is d. Half of it is d, and it is along y-axis. So it is dj mod cubed minus, because this is minus q, it is along that direction. So it is r plus dj divided by r plus dj whole cubed. And this whole thing is in bracket because this factor is the same for both. We are finding, of course, the field at point P, r, which is denoted by r vector. Now we assume that d, this distance is very much smaller than that distance. And we write down q times 2d. 2d was the separation between q and minus q, is equal to p, which is the magnitude of dipole moment. The dipole moment is a vector. It's given by the magnitude times the direction. The direction goes from minus charge to plus charge, and that is there. So it is from A minus q to P. We can simplify this expression, making binomial expansion of this denominator. This is squared, and keep d small. I can make a binomial expansion. I will not do the algebra here. It is worked out in NCERT book, class 12, chapter 1, for the case r equal to rj. And you can, it's not very difficult to do. For the simple case where this r is here, they have not worked it out for the general case, it is here. And the answer is given by 2p. So that you can see the field. Notice, if I take a point on the y-axis, this charge is nearer, so its effect will be larger. And this charge is slightly further away, so the effect will be less. So when I add the two, it will point along y, and that is along p. And that's what this says. It is 2p times r cubed. I will just quote the general expression. I encourage you people to work it out. I didn't want to do it because of the time constraint. It's worth doing this calculation once because it will help you in understanding how to handle vectors. If the students are given training to handle vectors, it will be very good in the long run. In the beginning, it's always a little difficult. All of us have, I certainly faced difficulty in the beginning, but once I got over it, I found it a very, very useful thing to do. So I encourage people to work this formula out. Notice the vector has two parts, one r vector and p vector. Okay, this is the answer. Notice if p dot r is 0, p and r are perpendicular, the field is along minus p. Let's see why. P dot r is 0, p is this way. If r were there, p dot r would be 0. Now the field here is in that direction. It is along minus y. Q, it is attractive, so it is along that direction. So when I add the two, the field will come along minus y. So that's the reason. Notice if I draw lines of force will come here, go like that. So line of force is positive here, and it is going in the opposite direction. So the electric field here will be negative. So that is that expression here. And I have written down r to the 5. A very important point worthwhile emphasizing is the electric dipole, the electric field due to an electric dipole for large distances is 1 by r cubed. Notice when r becomes very large, this is r squared, it becomes 1 by r cubed. This is not the case for a monopole. For a single charge, we all know it goes as 1 by r squared. That is because the charge, the electric field due to q and minus q try to cancel, and therefore it has become 1 by r cubed. It's an important point. Now, I have not given the general definition of a dipole. It was a simple example of a dipole, and I'm giving you the general definition of a dipole. It is, supposing I have a set of charges, qi, located at ri. I made a mistake. I should have written I here. It's 1. It should have been ri. I going from 1, 2, 3, n. There are n such charges, and they are located at ri. The dipole is given as sum of this. Remember, similar expression exists when we discuss center of mass. I write down M center of mass is given by an expression MI/Ri divided by the total mass. I'm not divided by the total charge. This is the dipole. For our simple case, let's work it out for the simple case. One charge minus Q is at minus dj, and the other charge is at Q at dj. One minus Q was at minus dj, and plus Q was dj. So it is minus Q times minus dj plus Qd. This is the answer. One more point. Note that the general dipole depends upon the choice of origin, whereas if the sum of the total charge is 0, then it does not depend on the origin. To see this, if I change my origin, Ri will change by some constant. Supposing it changes by a constant vector C. What is the extra but I get? I will get summation I going from 1 to n Qi times C. C is a constant. I can pull it out. So I will get the extra term will be C times Qi divided by I into 1 to, sorry, sum will be I going from 1 to n, C times Qi. But I have said the total charge is 0. If the total charge is 0, that term will be 0. So dipole moment does not depend upon the origin only if the total charge is 0. Now, why do we need a dipole? This is a very important thing. Why do we even talk about dipoles? And that is where the idea for a dielectric, it matters. And that's the reason I have developed it here. The concept is very convenient in understanding the behavior of insulators. It is used in parameterizing an insulator. Insulator, is bunch of molecules, and they have some positive charge and negative charge, as we know, nucleus and electron cloud. Supposing we consider an atom placed in an electric field, say between two parallel plates, having charges Q and minus Q. An atom has a positively charged nucleus and a negatively charged electron cloud. So when I apply an electric field, the positive charge nucleus will tend to move a little bit towards the electric field, and the electron cloud will move a little bit backwards. So the center of gravity of the electron cloud will be back, and the nucleus will move forward. So there will be a separation minus Q and plus Q, and that is the dipole. And the dipole will clearly depend upon the electric field that you apply. So if you apply small electric fields, then we can write as P as alpha E, and P is the dipole moment of a single molecule. It is called the atomic polarizability. So when we want to deal with a system like a dielectric, we will parameterize it by a bunch of dipoles and see how these dipoles add up to give us the correct electric field inside the dielectric. That's where the concept of a dipole is very useful. I'll just wait till you people read this out. This is the diagram I have here. The electric field here is 0. And I apply electric field. Notice this has moved a little bit. And here, that separation I've called D, not 2D. I've changed my notation. I've called this D. So there is a dipole. The force due to the external is balanced by the force due to the electron cloud. In this position, there is an attraction between these two. And that force, look at the charge here. It is getting attracted here, and it is getting moving towards that direction. Both of them must balance. And that's the equation that's being written here. Q is the force due to the applied electric field. And this, I have not done the calculation, is the force due to the electron cloud here. I have not given the calculation here. Again, I will encourage people to do it. Again, how do I do this? I assume the electron cloud is uniformly distributed here. So if it is uniformly distributed, I should be able to calculate the electric field due to the charges. And whatever be the charge inside, this distance D will give me contribution, and that is the field which you can calculate, and the answer is this. I've not written down the details. Okay. Now QP is QD. If I do that, I get 4 pi epsilon naught times E QD. If I write it in this form, just a minute, did I write it correctly? QD, yeah, Q by, did I miss an A cubed here? Yeah, I forgot an A cubed here. I should have written QE 4 pi epsilon naught E. QD is 4 pi epsilon naught, QQ cancels. I have QD, I should have written an A cubed. I forgot an A cubed, I'm sorry for that. But epsilon 4 pi epsilon naught A cubed, which I can write it as 3 times 4 pi A cubed by 3. This is the volume. V is the volume of the atom. So the atomic polarizability is given by this expression. It's a model. This gives a good order of the order of magnitude estimate. For example, alpha by 4 pi epsilon naught can be found from the experiment. I will not describe how the experiment for a gas neon. Our simple model gives this ticking works out to be 3 by 4. So we get 0.75, a factor of 2, but the order of magnitude is right. It gives an idea. Now, we will just assume that dipoles are formed. We are not interested in knowing the exact value of it right now. Now, here is my dielectric. And I apply an electric field. When I apply an electric field, the dipoles are all lined like that. A single dipole, I'm showing minus here, plus here. This is how a single dipole looks. So this plus here, minus here, and plus here cancel. So there is no charge here. The only place charge is left is on this side and this side. This is surface here. Okay, surface here plus positive charge. All right. Consider, this is what I have said. I will let you read it. I will just repeat here. There is no charge inside. Why? Because this is plus and this is minus and they add up to 0. Only place that doesn't happen is here where everything is negative and here everything is positive. And that's what is said in this slide. I will wait for some small time for you people to read it out. Okay, I'll now move to the next slide. Here it is. Consider a unit area here. I have written down, this is the unit area. P, the dipole moment. If N are the number of atoms per unit volume, the dipole moment is P is NP. And P I have written as alpha E. This already we know. This is the unit area and I am looking at this unit area. And this is the electric field that is applied. And this length is 1. I've taken this to be unit length. Yeah. This is my dielectric. All the dipoles, I'm assuming, are in the direction here. There are, of course, these are approximations. I will not get into the details of that. This is a very simple-minded calculation. Okay. You have seen the left surface is negative and the right surface is positive. This is negative and that is positive. There is no charge inside. We will now show the important result. The charge density here is P dot N, where P is the dipole moment per unit volume and N is the normal to the surface. We will show this result. This is a very important result. Notice we can relate P to the dipole moment of a single molecule. It is P is equal to N times P.
Excuse me, sir.
Yes?
Sorry to interrupt you, but there is some background noise from your side.
That is on the road. They are making some statements about corona that
Okay.
we should visit. It's a municipality with the speaker on.
Okay,
So I
okay,
think they
sir.
will go away in a few seconds.
Yeah, sure, sir. Okay, okay,
Right.
sir. Thank you.
Fine. I think now it's gone, most probably. All right.
Yes, sir. Now it is fine. Yes, sir. Thank you, sir.
Fine. Length of a dipole is d. So let me go back here. Each dipole is of length d. So how many dipoles can I arrange? In one, I can arrange 1 by d, right? The number of dipoles I will have is 1 by d. Let x dipoles per unit area be on the surface. That is, here there are x dipoles all lined up like that. There are x of these per unit surface. And there are 1 by d number here. So the total number of dipoles is x times 1 by d. And that is x by d is n. And sigma is minus qx. X is the number of dipole ends on the left side, minus q. And each has a charge q, minus qx. And qx is nd. Qd is Pn minus P. Thus, P is minus sigma. I can rewrite it as sigma as P dot N for the left surface. Notice for the left surface, I have N is in this direction, which is opposite to X direction. So my answer is in this direction is negative. So that negative sign is taken care of by P dot N. And that is the derivation which I have said here, which is very important. This is the crux of understanding how things work in dielectrics. This set of steps I have written down is the crux of understanding how to answer things in dielectric. Once this is done, everything else is straightforward. The polarization vector depends on the applied electric field. For small fields, we write it in this form. Chi E is called the electric susceptibility. These are a bunch of definitions. And of course, this will depend upon nature of the dielectric. Like alpha will depend upon the nature of the dielectric, or molecule in particular. Now let us take a particular case. A dielectric inside a slab, plate conductor. I have charge Q here, and I have put the charge Q is distributed over here uniformly. It's a huge plate, large plate, and sigma F is the charge density. This is called the free charge. I will explain why this is free. It is because I have the choice to put it. Depends on how much Q I put. I can manage this. Same way here. Now, on this side is the dielectric. There's an electric field here. That electric field produces dipoles all to be arranged, aligned. And we notice that there is no charge inside here. And there is just minus P and plus P here. This is not under my control. This the field does, and these are called bound charges because this is not under my control. So P is a bound charge produced by the applied field. I have only control over this. These are the free charges. This automatically develops inside the dielectric. There is of course no charge inside. It develops on the surfaces. And we have already found out what is this given by. P, the surface charge density here is essentially P dot N, and here also it's P dot N. N in this direction is here, so that's why it is positive. N is in that direction, and so that is negative. All right. Here, now, I can now solve the problem completely. I have here sigma F, one charge distribution, minus P here, plus P here. So I have 4 charge sheets. We did that in lecture 1. We repeat the same thing now. I have 4 charge sheets. E1, 1 is here, and E4, magnitude is just sigma F by 2 epsilon naught. Sigma F is the free charge here, minus, so I've written down the magnitude. Sigma 2 and sigma 3, 2 and 3, P by 2 epsilon naught. There are many equations in this slide, so it could be a little confusing. I will wait. I will again explain. I've drawn this circle to indicate where does this line of force come from. There are many, many lines of force. There are so many of them. So I want to tell you the origin of it. The red one at the top comes from this plate and it goes. Then the blue one, the next one comes from the plate, and that's all the field of lines of force are in that direction. And here, This one comes in that direction. And the last one comes in this direction. So I have here 4 chart sheets. And once I have chart sheets, I've broken all the problem into 4 chart sheets, and I can find the field here, I can find the field here, I can find the field here. So let's find the field at 3 points. Let's find it at A. A, notice I have this place, sigma F is in that direction. This is also in the same direction. Whereas, notice these two are in the opposite direction. One coming this way, the other coming this way. So these two cancel, whereas these two add. So I've written down sigma F by 2 epsilon naught minus 2 by P epsilon. P is the charge density here, plus 2 by P epsilon naught here, and plus 2, these two add. So this one and this one adds. These two cancel. And I've written the answer here. I will wait again because there are just too many things in this diagram. So people might like to stare at it for a few seconds and then see how the whole thing is. I'm almost through. I'll just... I found it at A. Now I'll find it at B. B, what is happening? Here, I have the field here, and these two both are opposite to that. So notice sigma F and these two add and these two subtract. So inside it is sigma F minus P by 2 epsilon naught. These two add, sigma F by 2 epsilon naught and sigma F by 2 epsilon naught add, and these two subtract coming from these plates. The bottom two, both coming from the dielectric surfaces here, 2 and 3, they both are negative, and so it is written here. And they add up to give me this answer. So the field inside, notice, is not sigma by epsilon naught, but P, so it is less. The field inside here is less. That's because of the shielding produced by this negative charge. Now the last point here. Here, what is happening? These two cancel, and here, okay, and I have here, wait, did I make a mistake here? Same thing, am I right? P, right. Something is strange here, C, and what happened? Excuse me, E is here. Is here. What is happening? This is positive and this is negative. Something is strange. P is here, here. Oh, the line of force here is in that direction. Sigma F here. Yeah, this is B. I'm sorry. E. E is here, right? So I have sigma by F by epsilon here, and then minus. So these two should cancel. Oh, this is outside. I have drawn C wrongly. C should have been kept here, please. Please, this C should have been here. Not, it must be between the dielectric and the plate. C should have been here. So these two add, and this here, these two cancel. Notice here and here, this C should have been inside, it's a mistake, and these two add, one coming this way, one coming that way. These two add, these two cancel. That's here. I will repeat it again. My C should have been here, not there. A, B, C was here, C went into the wrong place. Notice this C is inside the conductor, so this should give me 0. These two cancel, these two cancel. The way I've written C, the answer is 0. It is here, it is again sigma by P epsilon naught. I'm sorry for this. So we have the field inside the dielectric is sigma F minus P by I. I define a D, displacement vector, which is defined in your book, is epsilon 0 E plus P. everything is along the direction I. So if I take that, D is nothing but sigma Fi. We can get this result by writing the Gauss's theorem as S be a closed surface enclosing free charges and dielectrics, and the answer is this. Sigma QF is the free charge enclosed on a closed surface. It requires vector calculus to derive this result. I will not do this. We have just illustrated this by a simple example. Well, how do I get this? Because I take a pillbox here. Let me go back here. Here is a pill. I can take a pillbox. This is not the one earlier. Okay, maybe instead of going back, I will just show it here directly. I will take this, and I have this is my conductor plate, the leftmost plate, which is positive PQ, and I take a surface which is just inside, and then I take a pillbox, cylindrical pillbox of cylindrical outside here. It can be inside the dielectric. The answer is D. ds is given by QF. If I take a unit area, it is sigma F, and it is D times unit area is sigma F, and so I get D to be sigma F. So this is the generalization. I have taken a very simple example to show this. This is all in your text, and I think I will stop here. I thank you for the attention. Okay.
Thank you, sir. Thank you, Professor Mani, for
share
this.
now. Okay.
Either you or I can do that.
All right.
Yeah. Thank you, sir.
Yeah. Shall I click on that?
Yeah, sure, sir. You can take the question answers
I
from
will
the
read
question
the
answer
questions this
box.
time. Last time I didn't do that.
Yes, sir. Please.
Okay. Please explain induced field is non-conservative. When you mean by induced field, you are talking about Faraday's law, when there is a varying magnetic field which produces a induced field. There, what happens is when I have a field, the field is going around, it is an induced EMF which is produced. So it is like a battery, which is a continuous. Hello, can you hear me?
Yes, sir.
Yes, sir. Very much audible.
Pardon?
Audible, sir. You are audible.
Okay. Now, next is, please guide young researchers in India how can do research. Why people are doing good research from countries in USA. But this is a very, very difficult question. I'm not even sure. There are many people who are doing very good research in India also. It is not as if they are not. And I agree that we have to increase our quality and quantity. And that's not a very simple question for me to answer in such a short while. But I'm sure at some stage, Professor Vijay Singh, as a president of this, might even initiate some discussions on this in his magazine. All right. Next is, sir, are we pointing to real charge? Are we letting it as imaginary or image? No, the charge minus Q, which I wrote, was imaginary. It was an imaginary thing. All the charges occurring on the plate, negative charges are real. Moment I have a positive charge, the other things which are, here is my positive charge, and here all the negative charges are developed on the plate. And when we do it in class 8 or class 7, what do? I bring a positive charge. Positive charge attracts negative charge on this, and the positive charge left on the plate goes to the ground because it is earthed. That's what we say. And that's correct. Now we are giving a quantitative explanation of the entire thing. Okay. Now, if the conductor is not thick but thin, the field on the left-hand side is not zero, then no. If it is earthed, notice, if it is earthed, there can be no, here, I will again explain. This is an important question. Supposing this is the plate. I earth it. This potential is zero. So if there is a positive charge here, it will have to go to infinity, the line of force. If the line of force goes to infinity, this is at a higher potential, not allowed. So I cannot be left with any positive charge on the plate. It doesn't matter. Okay. Next question. Method of a unique solution for electric field and the potential. Yes, it does. Could there be two different representations of message change? No, that is where the uniqueness theorem comes. Can we get the field on the left-hand side of the image? No, left-hand side, the field is zero. We have already said it is inside the conductor. The field is zero. So there is nothing more to get. Is polar coordinates introduced in class 12 standard? I thought it would be. I do not know. I thought polar coordinates are there. But I have not immediately checked. Why can we not put image charges in the region where we are No, if I put the image charge there, that's a new charge you are putting there. So that means if I go very close to the charge, the field will be infinite. That's not a physical situation. Good morning, sir. Have doubt. The doubt is coming. Inside the electrostatic conductor, if the electric field is zero, then the potential is constant. Why potential zero is taken? Because I have assumed it is Earth, and I have assumed that the potential of the Earth is zero. So inside the electric, its only potential is constant. But if I keep it constant, notice everything will just increase by a constant, nothing more. Okay, clarify the difference between charge transfer and electron transfer. I'm not sure I understand the question. I'm not sure I understand the question. Perhaps the person who has asked this question should give me a little bit more explanation. He could send me an email and I will try my best. Is really the electron cloud, mean electron cloud moving in orbital are attractive to towards one side of the nucleus or the other side? No, that's a very simple model. Really, you will have to do a full quantum mechanical calculation to find out the displacement of the nucleus, which means you have to take the wave functions and work your way through. And that is, it can be done. It has been done. People, of course, do this in great detail. So classical model is this just model which was taking an electron cloud, one shifting a little bit, the other shifting and the other one. Okay, I didn't know this question. Can you please explain the electric susceptibility expression written in NCERT? I thought the one which I did more or less explained it, but if something which I said is not clear, please do send me an email and I will try to answer. Do homonuclear diatomic molecules like O2 act as dipoles? Can molecules that are not dipoles have polarizability? If there are situations in which that will not happen, there won't be any dielectric constant. It will be very small. But the answer is that if I apply an electric field to this, need not need intrinsic dipole moment. When I apply an electric field, automatically the nucleus will move one side. And if there is an intrinsic dipole moment, what will happen is the dipoles will, there is a torque on it, it will move towards the direction of the electric field, increasing the electric field. That can be calculated. I did not discuss that. What is the difference in electrical and magnetic susceptibility? I mean, significance of both. There will, one is for magnetic fields, essentially their magnetic moment comes from electrons going around in orbits, having currents, and that causes a magnetic dipole. And that magnetic dipole again can be aligned along the direction of the magnetic field. So in some ways it is similar, but in details they are very different. The kind of properties the magnetic moment show have very interesting ones like ferroelectricity, antiferromagnets, and things like that. There are such expressions in electrical susceptibility also, but they are not that common. Much more in spin-spin interaction is much more, effects are much more there in magnetism. Okay. Next is, I have a small question. You told that the charge has, charge inside a conductor is at a distance x 0. The plate x is 0. The x distance from Q to the point are defined certain distance on the surface of the conductor. Yes, I am talking about a point on the surface of a conductor and the distance of the P, where the charge is outside, and to the point on the conductor. That distance for the plate, x was 0. The coordinate x was 0 for the plate. Is it possible sigma f can be equal to P? No, that is not possible. Um, if it is, then that will make it a conductor. The dielectric will become a conductor. All the lines of force from sigma f will end on the place, and there will be no field inside. So that will make it a conductor. Can we assume uniform distribution of charge on dielectric? Uniform? No, yes, we can, because the electric field is, these are all infinite plates. We are thinking in terms of infinite objects to simplify the mathematics. If I had to do things in finite along y and z direction, the mathematics will get complicated. But the physical ideas are the same. Whenever we do physics, we have to simplify into a physical situation, and then when actual engineering comes, then you have to take into account by appropriate modeling and doing experiments. These concepts work quite well once we know how to apply them. What are the bases for defining displacement vector? That is a very useful concept to generalize the Gauss's theorem. Once I use the Gauss's displacement vector, I need to know only about the free charges. I don't need to know about the bound charges. So I can find out D for using the free charges. Once I have found out D, I can find out E, because D is related to E by a constant. And of course, dimension constant, but you can immediately get that. That's why this is a very useful method of doing things. Define charge, and only two types of charges are there. Three? No, not in electromagnetism. There are only two kinds. In quarks, there are colors, as they call. They are color charges. One can have 3, 4, and so on, different kinds. But here, experimentally, we have only two kinds. How can physics be interesting for students who are really afraid of it? It's a very, very big question, an extremely difficult question to answer. Again, I would appeal to the president to look at these things, which are very important for the development of physics in the country. No question. If we place a negative charge in front of a conductor, the calculations can be done by, of course, I've just put a positive charge. You can change everything by minus sign and everything will work out. Exactly the same. Q, whether Q is positive or negative, it doesn't matter. At no stage it was important for me to make Q to be positive. Can you put some light on electric displacement vector and what is needed to introduce it? I introduced it in the example. More or less the same thing is done in NCERT. If you want to introduce it more strictly, more rigorously, I'm afraid you need vector calculus, which is beyond the reach of school mathematics. So we cannot do much more than that right here. But I can look up this page 77 and respond to you if you send me email, and I will check exactly what more we have. What can we not, why can we not put image charge in a region where we are calculating? I had answered that question. Thank you, sir. Enjoyed. All right. So one property of electric field is that it cannot have a direction which is kind of a closed loop for a single charge. It violates, yes. Why? If I go around in a circle, then I will go from a higher potential to a lower potential. I go on coming back to the same point. Same point is at the same potential. So I will not be able to do that. How to understand a single charge possesses a dipole moment? That is the point. If the charge is not located at the origin, but on a slightly away, the electric field, which I can calculate, can be broken up into field due to a monopole plus field due to a dipole and so on. Gaussian surface cannot pass through discrete charges. Why? Because if I make a Gaussian surface pass through a discrete charge, the electric field there will be infinite. So how do I take E dot ds? The limit is a major problem. Why magnetic monopoles don't occur? That is a big question. There are models which show the magnetic monopoles are very, very heavy, and that could be the reason why is not that much produced when the universe started, and so on. But there's no simple answer to that. Lecture 1, I'm sure Dr. Poonam Jain will be able to help you. Can I get the, I can find the potential charge alone. Right, I missed. Okay, you can get it there. What will be the electric field along the diameter of a ball which is uniformly charged? That is not a very straightforward, easy question to answer. It requires a reasonable amount of mathematics. Why only charges, 2 charges are there? I don't know the answer to that question. Yes, sir. Okay, but please send me the email. I will not be able to keep this with me. Please send me an email. I have already sent you the email in my slides, hsmoney@gmail.com. What type of forces occur in a dielectric medium? We have discussed the forces. Forces we have not discussed. That will depend upon the force acting on dipole, which is not what I've discussed. It will, we need to discuss that a little bit more at length. It is forces on dipoles. Yes, the answer is electric. The H, the corresponding equation comes to be for free currents. Just like this comes for free charges, corresponding equation for H comes from free currents. Okay.
Sir,
I guess that finishes all the questions as far as I can see.
Yes, sir. Sir, few of the participants are asking question on YouTube. So may I take the question for you?
Okay. Where?
Yeah. Yeah, sir. I can read that questions from
right.
the YouTube channel.
Okay.
The question is from Mr. Ajit. He want to ask, is there some limiting distance or a maximum distance for 2 objects in which 2 bodies can show induction? Am I clear, sir?
Yeah, you are clear. But induction, in what way are we referring to? Induction in magnetism or electrical? I don't understand.
Okay.
Can you
So,
request the person to put the question in Gmail for me?
yeah.
Okay.
I request Mr. Ajit, kindly put your question clearly in the Gmail ID of Professor H.S. Money. I will be share his email ID in the chat box. Thank you. Sir, another question is from Mini Krishna. She is asking, if we place a negative charge in front of the conductor, the calculation can be done by the method of images?
Of course, because just change Q to minus Q in all the calculations.
Okay, thank you, sir. Another question is from Toshif Parvez. He want to ask, could you please explain why the force on the plate per unit surface area is sigma times E by 2?
I went through that explanation in detail. Again, I will ask him to see my first lecture, the last slides, where the electric field due to the rest of the surface is half the electric field due to the one which is nearby. And it is the electric field due to the other set which should matter. You should not calculate the force using this due to the charge itself. It has to be the other set. If I have 2 charges, Q1 and Q2, the force on Q1 is due to the field due to Q2. So if I take a point P or a surface, I should not take the self force. I have to take the force due to the rest of the surface. And that produces just half the field. Okay.
Okay, thank you, sir. No more question on the YouTube channel. Thank you so much. Now the session to Dr. S.K. Singhal.
Thank you, sir. Professor Mani, for beautiful lecture, wonderful lecture you have explained today about the electrostatics. And many doubt that we have are clear now about this concept. Now I request Shri R.K. Tiwari, sir, Vice President IAPT RC1, to propose vote of thanks. R.K. Tiwari, sir.
थैंक यू डॉक्टर सिंघल, सभी को नमस्कार। मैं आर के तिवारी, वाइस प्रेसिडेंट IAPT RC1, अपने RC1 की ओर से आप सभी का हार्दिक अभिनंदन और धन्यवाद देता हूं, और खास तौर से प्रोफेसर HS मनी जी, सर आपका बहुत बहुत धन्यवाद, क्योंकि आज आपने हमारे लॉकडाउन डेज को भी बहुत अच्छा बना दिया। एज यू नो, UP is under lockdown for 2 days, Saturday and Saturday, complete lockdown, Saturday, Sunday. So you have made our day very useful and very ज्ञानवर्धक। तो आपका बहुत बहुत धन्यवाद कि आप आए और आपने इतना अच्छा लेक्चर दिया। इसी के साथ साथ मैं धन्यवाद करना चाहूँगा हमारे श्री प्रोफेसर विजय सिंह जी का, जो हमारे प्रेसिडेंट हैं, IAPT के नेशनल प्रेसिडेंट हैं। मैं धन्यवाद करना चाहूँगा आनंद कुमार जी का, प्रोफेसर आनंद कुरियन जी का, मिसेस प्रज्ञा करीम जी का, सहजवानी सर का, प्रोफेसर अजय घटोक जी का, प्रोफेसर BK शर्मा जी का, इन सभी का बहुत बहुत धन्यवाद कि आप लोगों ने हमारी इस वेबिनार को सुनकर, देखकर इसका मान बढ़ाया। इसके लिए हम आपके बहुत बहुत आभारी हैं। दिल्ली साइंस टीचर फोरम की ओर से मैं PC घोष जी का, वार्ष्णेय जी का, कन्हैया लाल जी का, श्रीवास्तव जी का, डॉक्टर अनिल वशिष्ठ जी का बहुत बहुत धन्यवाद करता हूं कि वो आए और उन्होंने अपना सहयोग हमें दिया। ये एक जॉइंट वेंचर है, DSSTF और IAPT दोनों ही बच्चों के लिए और छात्रों के लिए और टीचर्स के लिए काम करते हैं, और मेरा सौभाग्य है कि मैं दोनों संस्थाओं से जुड़ा हुआ हूँ। ये बहुत सौभाग्य की बात है कि आप सब आए। इसी के साथ साथ मैं धन्यवाद करना चाहूँगा अपने पूर्व प्रेसिडेंट डॉक्टर OP शर्मा जी का, अपने प्रेजेंट प्रेसिडेंट प्रोफेसर वेद प्रकाश श्रीवास्तव जी का, श्री अनिल कुमार जी का, अपने एक्स सेक्रेटरी रवि भट्टाचार्य जी का और रमनीक कपूर जी का। इसी के साथ साथ धन्यवाद मैं करना चाहूँगा गिरी भारद्वाज जी का, सीमा वत्स जी का, HK सिंधवानी जी का, राजीव त्यागी जी का, मनोज कौशिक जी का, अजय गर्ग जी का, डॉक्टर DK पांडे जी का। ये हमेशा हमारे लिए तैयार रहते हैं, जब भी हमें कोई जरूरत होती है तो DK पांडे जी हमेशा तत्पर रहते हैं IAPT की सेवा करने के लिए। मैं धन्यवाद करूँगा जयवीर सिंह जी का, विकास मित्तल जी का, राकेश भारद्वाज जी का, RK त्यागी जी का और AK पांडे जी का, गिरी भारद्वाज जी का, और खास तौर से जो हमारी टीम इस समय काम कर रही है, टेक्निकल टीम, जिसमें हमारे सेक्रेटरी डॉक्टर भंडारी जी हैं, डॉक्टर पूनम जैन जी हैं, डॉक्टर योगेश जी हैं, डॉक्टर सिंगल है, ये हमारे ट्रेजरार भी हैं। और आप जानते हैं कि बिना ट्रेजरार को धन्यवाद दिए कोई कार्य सफल नहीं होता है, तो ट्रेजरार साहब का बहुत बहुत धन्यवाद। मैं वंदना बागा जी का भी बहुत बहुत धन्यवाद करना चाहूँगा, और इसी के साथ साथ मैं ये आशा करता हूँ कि जब भी हमें आवश्यकता होगी डॉक्टर प्रोफेसर HS मनी जी आएंगे और हमारे जो डाउट है उनको समय समय पर दूर करते रहेंगे, जिससे कि जो भी कार्यक्रम हम बच्चों के लिए करते हैं उसमें हमें पूरा सहयोग मिल सके। मैं एक बार फिर आप सभी का धन्यवाद करता हूं और आशा करता हूं कि अब ये जो सिलसिला शुरू हुआ है ये रुकेगा नहीं। हम तो अकेले ही चले थे जानी में मस्ती मगर, आप लोग मिलते गए और कारवां बढ़ता गया। ये जितना भी प्यार से हम दिल्ली साइंस टीचर फोरम और IAPT काम कर रहा है, ईश्वर इसी तरह हम दोनों का सहयोग बनाए रखे और हम फिजिक्स के और साइंस के हित में लगातार आगे बढ़ते रहे। यही मेरी शुभकामनाएं और ईश्वर से प्रार्थना है। आप सभी का बहुत बहुत धन्यवाद। सो नाइस ऑफ यू फॉर मेकिंग आवर डे वेरी प्लेजेंट एंड नॉलेजेबल। सर, मणि सर, आपका अगेन बहुत बहुत धन्यवाद, और हम चाहेंगे कि आप आगे भी अपना आशीर्वाद हम सबके ऊपर बनाए रखें। बहुत बहुत धन्यवाद आप सभी का। मैं अब आगे पूनम जी को कार्यक्रम के लिए आमंत्रित करता हूँ। पूनम जी।
Thank you, Tiwari sir. One paints the beginning of a certain end, the other, the end of a sure beginning. With this, I would like to thank our eminent speaker, Professor H.S. Mani, for the enlightened lecture. It is my pleasure that he has accepted our invitation and delivered such an informative and wonderful talk. Thank you so much, sir. I am grateful to all the distinguished guests, Professor Vijay Singh, Professor Ravi Bhattacharjee, Professor Ajoy Ghatak, Professor B.K. Sharma, Dr. D.K. Pandey, Dr. Anil Vashisht, Shri P.N. Varshne, and all the panelists who are present over here. I am also grateful to all the members of Indian Association of Physics Teacher Regional Center 1 and the Delhi State Science Teachers Forum and wonderful participants for their patiently listening to the proceedings of both the events of this series. Thank you for your contribution in making this webinar again a success. Thank you so much. Now, I want permission from our President, Professor V.P. Srivastava, to signing off it formally. May I, sir? Srivastava, sir, am I audible to you?
Yes, 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 please.
Thank you, everyone. Have a great day.
Thank you very much. Thank you, sir. Thank you, Srivastav, sir, for this privilege. My
Thank you very
regards to
much.
Professor
Thank you,
Vijay
everyone.
Singh and Professor Mani.
Thank you.
Thank you. Thank you.
Thank you.
Hearty
Thank you,
congratulations
everyone.
for a wonderful program. It was really wonderful
Thank you.
today. We really enjoyed, all of us. Thank you so much. Thank you.
Thank you, Varshni, sir. Thank you very much.
everyone.
My
Thank you.
regards.
Thank you, Poonam Madam, and thank you, Professor Manish. Thank you.
Thank you, Dr. Vijay Singh, sir. After seeing you after many years of IIT Kanpur. Thank you very much, sir.
You are not audible, Poonam ji. You are
Yes,
not
sir.
audible.
Yes, sir.
Can we leave?
Yes, sir. Yes, sir. I'm just saving the video so that it will be saved on my computer and then I will end the meeting. Yes, sir.
Okay,
Yes,
okay.
sir. Hardly 2 minutes. Yes, sir.
अब ठीक है?
Yes, sir.
ठीक है।
Okay, sir. Finally ending the meeting. Thank you so much.
Thank you.
Thank you.